Okay guys, we're back again with the second part of the aromatics booklet. So we've got electrophilic substitution. This is the mechanism that aromatic compounds are going to undergo. So just a reminder of the mechanisms that we've covered. If you have anything that's nucleophilic, nucleophiles are when you have electron donors. So aromatic compounds have this area of high electron density, which means they are going to repel. So they're not going to undergo nucleophilic reactions because they're going to repel the nucleophiles. So the delocalized electron cloud above and below the benzene ring is an area of high electron density. Since it contains the 6 electrons. As a result, benzene is open to attack by electrophiles. So electrophiles are electron acceptors. So these either need to be positively charged species or species that have a partially positive charge. Although the molecule is quite unsaturated, the main type of reaction is not addition. So we've come across addition reactions when we looked at alkenes. They underwent electrophilic addition. This would remove the delocalization, which makes the ring more stable. So as a result, the type of reaction shown by benzene is mainly substitution. So there are going to be 3 types of reactions we're going to look at using electrophilic substitution, which you're going to cover, and you need to know the reagents and also how we produce the electrophiles. So there's an extra equation that's needed for these. Okay, so the general mechanism then is exactly the same. The only thing that's going to be changing are the reagents that we're using. So we'll go over the general mechanism first. When an electrophile approaches the delocalized cloud, a pair of electrons from the cloud is detached to bond to the nearest available carbon. So remember, these curly arrows represent the formation of a covalent bond, and they always go from electrons to something positive or a bond to something positive. This forms an unstable intermediate, which the delocalized ring is partly broken. So we've gone from here where we've got our full ring, and then we're forming a covalent bond to E+. This is your electrophile. And then we get our intermediate ion. Okay, so this is our little middle step before we get to the product. So in this ring, each carbon is bonded to a hydrogen, so that's this hydrogen here, and then this is the new covalent bond that's formed to this. Okay, so because the molecule effectively gives the electrophile an electron, a positive charge is established on the intermediate, which is just here. The ring is shown to be broken and must not extend near the carbon where the electrophile attaches. So these 2 points adjacent to where the electrophile has attached, the ring should not extend, so go higher. The unstable intermediate then breaks down by taking the electrons from the bond to the hydrogen, using them to reform the delocalized ring. So this is where we're saying it's substitution. We're not adding, so going from double bonds to single bonds, and we're not eliminating a small molecule. We're keeping the same number, so it's substitution. So the electrophile is substituting this hydrogen atom. So the third step then is to show that this covalent bond breaks and the electrons go back to the ring to reform the delocalized ring of electrons. So this is our product. So really, the electrophile would be drawn like that. These 2 steps are common in all electrophilic substitution reaction mechanisms. The main difference lies in the nature of the electrophile and how it forms. Practice drawing the mechanism below by combining the 2 steps in one line. Okay, so we've got our benzene ring. Then we have our positive electrophile. The arrow starts at the ring and goes towards the positive charge. Then we get our intermediate ion. Where now we draw the hydrogen bond and the electrophile. Because it's bonding here, the horseshoe has to point in that direction and it cannot extend over these 2 points. So this would be the highest that it can go, and then we have a positive charge. So this would be mark 1, this structure would be Mark 2, and then the covalent bond here is going to break and the electrons come back in to reform the delocalized ring. So that would be Mark 3. And then we have our substituted ring, and we have the H plus ion that's been lost. Okay. Okay, so the first mechanism we're going to look at, or the first use of electrophilic substitution, is the reaction nitration. So benzene can be nitrated by reacting it with concentrated nitric acid in the presence of concentrated sulfuric acid at 50 degrees. The mixture is sometimes called a nitrating mixture. So in terms of reagents, you have to say conc nitric acid and conc H2SO4. Okay, so the nitric acid is actually what's going to produce the electrophile. The H2SO4 is acting as a catalyst. So here is the equation to show the production of the electrophile. So we've got nitric acid and sulfuric acid, and then they react to give NO2 plus, HSO4 minus, and a molecule of water. So here, this NO2 plus is the electrophile. So it's the positively charged species. The HSO4 minus, we're going to show later how this can reform the H2SO4, because obviously a catalyst has to be regenerated at the end of the reaction. So the NO2 plus is the real electrophile in this reaction. It's called a nitrile cation. Don't confuse this with a nitrile group of CN. Its old name was the nitronium ion, which you may still encounter. I would say nitronium ion. The NO2 plus only forms in large quantities if concentrated sulfuric acid is present. In pure nitric acid, there's very little, and this explains why the reaction is very slow with this reagent alone. So if you want to increase the rate of reaction, we need to ensure that we've got the concentrated sulfuric acid present. So here's the mechanism for nitration. Now, it's exactly the same as before, except instead of saying E plus, we've actually got the NO2 plus as our electrophile. Now note that the bond here is being formed to the nitrogen of that. So when we actually show our intermediate ion, we've got N here, so the nitrogen, that's where the bond is to. Now it loses its positive charge, and then that's shown here in the delocalized ring. So it's broken and it adopts this positive charge. And then your third mark, the covalent bond breaks, so the arrow goes, the curly arrow goes from the bond into the ring towards that positive charge. And then this is our product. So again, just to avoid confusion, that would actually be a bond drawn like that. The H plus ion that's formed, so this is the H plus ion that's been lost here. Now if you remember from earlier, when we formed the electrophile, we had this HSO4 minus ion. So to reform the catalyst, the H plus that's been lost from here is going to react with the HSO4 minus, and we will end up with our H2SO4. So we've regenerated the sulfuric acid catalyst. So why are nitration reactions important? They increase the reactivity of the molecule. So aromatic nitric compounds tend to be very explosive. The most familiar example is this. So this is TNT. Okay, so trinitrotoluene. The systematic name, or the IUPAC name, if this is carbon 1, then we would have 2, 3, 4, 5, 6. So 2, 4, 6 trinitro. Oh wait, it's alphabetical. So in terms of naming this then, it's going to be alphabetical. So we've got 1 methyl, 2, 4, 6 trinitrobenzene. Old name is trinitrotoluene, and then that's TNT. The addition of this methyl group is what makes it susceptible to further substitution. So you would nitrate it once, so you'd have methylbenzene, and then you would do nitration once, and then it could be nitrated again and again. Our other uses at the bottom here, so dyestuffs, benzene obtained from natural sources is first nitrated to nitrobenzene, and then this is reduced to phenylamine, which is the starting point for the whole series of coloured dyes called aniline dyes. These were amongst the earliest synthetic dyes ever made. So phenylamine, instead of having a nitro group, we would have an imine group. So we're going to look at that reaction whenever we look at imines later on. Okay, the second reaction then using Friedel-Crafts is acylation. So an acyl group is where we have a carbon with a carbon double bond present. So in this reaction, ethanol chloride, so we've come across this when we did carbonyls. So this is ethanol chloride. So acyl chlorides are where you have a carbonyl group with a chlorine attached. This chlorine means that they're really, really reactive because this is much more electronegative, which leaves this very delta positive. So acyl chlorides we've covered when we did nucleophilic addition elimination reactions in carbonyls. So in this reaction, the ethanol chloride needs the aluminium chloride catalyst and warming to put the acyl group into benzene. The product is one of those where the name cannot be based on benzene since there is no specific name for the COCH3 group. So the main chain is named ethane based on the 2 carbons in the acyl group. The functional group phenyl and ONE are used to give the final name of phenylethanone. So our product here, I'm just going to draw it to the side so that you can see it. So we've got a carbon with a carbon double bond and then a CH3. So ONE is used because actually this would be described as a ketone group. So we've got ethanone, and then here, instead of saying benzene, because you can't say ethanone benzene, we're going to change this to a prefix and it's going to be phenylethanone. Now, just because I've drawn this off to the side doesn't change the actual numbering. We would still I've just done it in a different orientation. So this is still carbon number 1. So this is the same as if I drew it. This is the same thing as this. Okay, so again, we have to show an equation to produce the electrophile. The catalyst is the same, so there's only one catalyst that you need to learn for the Friedel-Crafts reactions. It's AlCl3. So again, if we were going to draw this or write this as an equation, we'd have CH3 COCl plus AlCl3, and that produces CH3CO plus and AlCl4 minus. Now I've put the positive charge on the carbon. In your notes it actually shows the carbonyl bond. You can do either as long as the positive charge is on the molecule. That's the important thing. So here again, this positively charged species is the electrophile. So then we've got first arrow going from the benzene delocalized ring to the positively charged part of that molecule. Now I'm going to draw this one out again at the bottom because this is an alternative way to draw it. So we have H3, not Cl. Okay, so we've got the COCH3 and this is the positively charged part. The arrow goes from the ring to the positive carbon. Then we have our hydrogen, and then here that's formed a bond to the carbon. Sorry, that's really wonky. There we go. And then this comes back to reform, so the electrons are coming back to reform the ring, and we've lost the hydrogen. And then we get the H+. So again, we need to show how we can reform the original catalyst. So that H+ is going to react with the leftover AlCl4 minus, and we're going to reform the AlCl3 and a molecule of HCl. Okay, so a second use of electrophilic substitution are in Friedel-Crafts reactions. So we're going to look at two of these, alkylation and acylation. So alkylation is placing an alkyl group onto the benzene ring. Remember that benzene has to lose a hydrogen so that the group can attach. This is where we're substituting the hydrogen. So the usual example of alkylation is using chloromethane, which would form methyl benzene and then your byproduct here of HCl. So for this reaction then, exactly the same as nitration, we have to show how we can form the electrophile, and then we do the mechanism as well. So for Friedel-Crafts alkylation, what they discovered was the reaction wouldn't work unless the conditions were completely dry and warm and some aluminium chloride catalyst was present. Now the AlCl3 has become known as the Friedel-Crafts catalyst. So the mechanism for the reaction must be understood. So we've covered that already, so we're going to have a look at how we can adapt it to this reaction. So initially the catalyst and reagent interact to produce the electrophile. Aluminium chloride is the catalyst and attaches itself to chloromethane, polarizing the CCl bond to the extent that it forms a CH3 plus ion and an AlCl4 minus ion. So here this is the electrophile. The positively charged species is the electrophile. Now if you were to write this as just an equation, we would have AlCl3 plus CH3Cl produces CH3 plus, so this is the electrophile, and AlCl4 minus. Always remember the charges on these ions. So the mechanism for this then, exactly the same as before, but instead of E plus or NO2 plus, we're using the CH3 plus. Then we have our curly arrow coming back into our intermediate, and then we have our product. So again, this you can draw it as a bond. So at the bottom then, you're showing the reforming of the catalyst. So we get the AlCl4 minus that was from the first reaction here. That then reacts with the H plus that's been substituted, and we get HCl and AlCl3. Now, things that you would observe, HCl, we would see misty fumes. This is acidic as well, so we've got an acid being produced. So again, we can say that it's corrosive, so that would be a negative for that. Okay, so following on from that then, I thought we'd look at a couple of questions from the question booklet. So the first one then is just question 1. So acyl chlorides such as CH3, COCl are useful compounds in synthesis. So always make sure that you know what that actual compound looks like. So CH3, COCl, we've got a double bonded carbon here and then a chlorine attached. So the acyl chloride, and this is ethanol chloride, reacts with benzene. Write an equation for the reaction and name the organic product. So there's two ways you can do this when it says write an equation. You can either give the actual structure for benzene and then our CH3COCl, and then that would produce C double bond O CH3 plus a molecule of HCl, or you can give it as the structural formula. So benzene is C6H6 plus CH3COCl, and then here when we're writing the structural formula for this, it becomes C6H5 COCH3 plus HCl. So either this or this will be fine. Identify the catalyst for the reaction, and the catalyst is AlCl3. Write an equation to show how this catalyst reacts with the ethanol chloride to produce a reactive intermediate. That reactive intermediate is the electrophile that they're asking about. So here it would be CH3COCl plus AlCl3 produces CH3CO plus and then AlCl4 minus. Okay, name and outline a mechanism for the reaction of benzene with the reactive intermediate. So name of mechanism, electrophilic substitution, And then the marking points then for this. Mark 1 is for the arrow going from the ring to the positively charged carbon. Mark 2 is for your intermediate ion. And then mark 3 is for the arrow coming from that bond back to reform the delocalized ring. And you don't need to draw the product for this either. Okay, here I've moved on to question 2b. So benzene can be converted into amine by a two-step synthesis shown below. So we're actually focusing on this reaction here in this question, reaction 1. So the mechanism of reaction 1 involves attack by an electrophile. Give the reagents used to produce the electrophile. So both reagents are needed, and we have to say concentrated nitric acid and concentrated H2SO4. You will be marked down if you miss the concentrated out. Write an equation showing the formation of this electrophile. So we've got HNO3 and H2SO4 will produce NO2 plus HSO4 minus plus a molecule of water. Outline a mechanism for the reaction of this electrophile with benzene. So exactly the same as the previous question. We start off with our benzene ring. Our electrophile is now NO2 plus, so the arrow goes from the ring to the positively charged nitrogen. Oh gosh, that's our intermediate. Ignore that I joined that up, it should be a horseshoe. And then our second arrow comes in here, so that would be your 3 marks. Let me just redraw that. So that's your intermediate structure, and then our arrow comes in there. So 6 marks for that, 3 for the mechanism, and then 3 for the reagents and the equations. So I don't think these are particularly difficult.